Okay, perfect.
Okay, so thank you very much for giving me an opportunity to present this work today. So I'm going to talk about deep learning algorithm for the reconstruction of TeV-PeV cosmic rays in space. So first, I'm going to spend a few slides to describe the instrument that we work with, actually instruments, and the type of physics problems that we address. So I guess this is something not very common to LHC people, so I'll just explain the type of experiment. So our major instrument is called Dark Matter Particle Explorer, or DAMPE. It's a satellite particle detector which was launched in 2015 from Gobi Desert in China, and since then it successfully collects data operating on sun synchronous mode in a sky survey regime. So DAMPE payload consists of 4 main subdetectors. In the core of the detector, there is a, can you see my pointer actually? Okay, I'm not sure. So in the core of the detector, there is a bismuth germanium oxide colorimeter, which is about 30 radiation lengths, and it is the thickest colorimeter ever used in space. It allows to measure electrons and gamma rays up to 10 TeV and protons and ions up to about 500 TeV. Then there is a silicon tungsten tracker converter, which consists of single-side silicon strip detectors with a position resolution of about 50 microns. So it serves for reconstruction of cosmic ray trajectories, for the identification of the direction of incoming gamma rays, and for the measurement of the particle absolute charge. Then there is a plastic scintillator detector, which again serves as an instrument for absolute charge identification in a very broad dynamic range up to nickel. So it's able to measure iron and nickel. It also serves as an anti-coincidence detector for gamma ray detection. And finally, there is a neutron detector serving as an additional electron-hadron discriminator. So the major physics goals of DAMPE are measurement of cosmic ray electron plus positron spectrum, and this was the first paper published in 2017 in Nature. This unique measurement spans 3 orders of magnitude in energy and reveals for the first time structure in the spectrum, which is attributed to the local nearby cosmic ray source. Then the next result was the measurement of cosmic ray proton spectrum up to unprecedented energy of 100 TeV. And then it was followed by the cosmic ray helium spectrum measurement, which you see on the left in this slide. And again, it also reveals structure in cosmic rays at highest energies. Combined with the proton spectrum, it indicates of a likely new source of cosmic ray acceleration. So these 2 measurements, proton and helium cosmic rays, will be in the focus of my talk, and the physics focus, while I'll be talking about technical things. This is our ultimate thing. We want to extend these measurements further. Also in DAMPE, there are other measurements being performed, like cosmic ray ions, carbon, oxygen, iron, etc. So DAMPE is the state of the art in cosmic ray detection at highest energies. Now I'm going to spend a slide talking about the future, which is the high energy radiation detector mission, which will be launched in 2027. In some way, it's considered a successor of DAMPE. It shares similar detector design ideology, where you have thick colorimeter in the center. But interesting feature of HERT is that it will have tracking devices, either silicon trackers or scintillating fiber trackers on 5 sides of the detector, while on DAMPE we have it only on 1 side. Also, this detector will be bigger, and because of that, and because of this 5-side tracker, it will have much larger acceptance. Another interesting feature of HERT is that it will have a 3D imaging colorimeter consisting of LISO cubes. So this will be a first 3D colorimeter in space. All this would allow HERT to do things which we cannot think about now with current experiments, like, for example, measuring cosmic ray electrons up to 100 TeV and protons and ions up to few PVs. So this is the region where the transition between galactic and extragalactic cosmic ray happens. So this is a very interesting physics that we are currently doing with DAMPA, and we're going to do with HEVT. Okay, so I introduced the experiments now, getting actually to the data reconstruction and tracking. So first I will explain how standard tracking is currently done in DAMPA and why tracking is important. So, our conventional tracking algorithm follows the usual scheme that you use in space astroparticle experiments. First, you fit the shower axis in the colorimeter to get a tentative particle direction, and then you use this direction as a seed for tracking, for pattern recognition in the tracker. Namely, you do a loop over possible track candidates starting from heat in the first or the last layer, and then you fit a track candidate which is compatible with the colorimeter hypothesis, initial colorimeter direction. So you have a loop of all possible combinations. In DAMPA, we do it separately in two projections of the detector, and then it's combined in a single 3D track. Until recently, this algorithm was serving us relatively well, so it's quite stable, but it has its problems, and it will not be sustainable for the future. Among the problems are the fact that, as you can see in this figure, there are gray lines represent reconstructed tracks. So you have many track candidates, while you have to select only one because you have only one cosmic ray that passed through your detector. So it's a needle in a haystack problem eventually. Second is that this algorithm is also computationally expensive because we do a lot of combinatorics here. And finally, it's not efficient at highest energies because when the heat multiplicity is very high, efficiency of this algorithm drops, as you will see. So tracking becomes really a challenge as you move towards PV scale energies. Why tracking is important? Because we use track for absolute charge identification. So far in DAMPA, the usual strategy is that you take a track reconstructed in the tracker and you project it onto the plastic scintillator detector. The thing is that the size, the sensitive unit of plastic scintillator detector is big. It's around 2 centimeters. It has a width of 2 centimeters. So even if you are slightly wrong with your track, which I remind you has a tracker has a resolution of 50 microns. Even if you picked up a wrong track, but as long as it's close enough to the real track, it will not be a problem because it will still point to the correct plastic scintillator bar and you will identify charge. But there is a problem. So as you can see, the distributions in the middle, it shows the proton and helium absolute charge measured in plastic scintillator at 50 TeV and at 500 TeV. And you see, when you move towards 500 TeV, 1 PV, the proton and helium signals are completely washed out. This happens because you have a backscattering of particles from colorimeter at these energies, and it contaminates the signal. On the other hand, you could do the job of absolute charge identification directly in the tracker because your silicon also measures d/dx, so you can measure absolute charge there. And on the plots on the right, you see that you can do it much better than with plastic scintillator. However, there is one trick in this plot. Here we use a true particle direction. So this is not a reconstructed track, this is a true direction. So assuming that we can perfectly reconstruct the track, we can have a perfect proton and helium signal. Now, what we have with the current existing algorithm, standard algorithm, you can see on the distributions in the middle, again, for 2 different energies, 50 TeV and 500 TeV, standard tracking doesn't do a very good job, especially as you move towards PV energies. Here, there is a standard tracking and also standard track identification, because as I told you, standard algorithm reconstructs multiple track candidates, and then you need to select one. Also on the plot on the right, you see what you would get with the standard tracking, but assuming that you can ideally perfectly identify the correct track from the ensemble of candidate tracks. So this ideal selection, basically on the Monte Carlo truth level, we take a reconstructed track which is closest to the truth track. But even in this case, at PV energies, you see this is bottom right plot, you see a long tails of proton helium distributions. So if you want, with this existing tracking paradigm, if you want to do PV scale measurements of cosmic rays, you will face very large systematic uncertainties. And that's why you absolutely need a new tracking algorithm to perform such measurements. Now I'm going to talk about the actual algorithm that we developed. So naturally, the first thing that we want to improve is the colorimeter seat. So we ask ourselves a question: can we fit a shower direction better than you do with the standard analytical methods of shower momentum, fitting, etc.? So our approach is based on convolutional neural nets. So we take an image of a colorimeter and combine two projections. So here on the plot, you see XZ and YZ projection. We combine them in a single image. That's why it looks as a passage of two particles. These are just two projections of one particle. We feed this image into convolutional neural net and ask it to predict 4 variables that you can see on the plot here. This is the coordinate of a particle in the top layer of the tracker, X and Y, and the coordinate of a particle, of a primary particle in the bottom layer, X and Y. So you have 4 variables to predict by this network. In this plot, you see the architecture of the neural network. So every pixel on the image goes from 0 to 1. So it's normalized to a maximum signal, in the maximum colorimeter bar signal in the event. Then it's followed by 3 convolutional layers. And then you have multi-connected layers, fully connected layers, sorry. As a target loss, we use mean squared error, and the network is trained purely on Monte Carlo. We use around 3 million of events. Also, I should note that we do different trainings for high energy domain, which is about 1 TeV, and low energy domain. And another feature, as you can see, in the output of the network, you have what is called MC model and data model. So there is an additional layer, which we call data model. This is a linear layer with linear activation, which we train separately on the data. And the purpose of this layer is to perform alignment between colorimeter and tracker, because your neural network predicts direction from the colorimeter, but then in real data, colorimeter is not perfectly aligned with the tracker. So you want to, if you want to predict something based on colorimeter on the tracker level, you need to do the alignment. And this layer is trained separated on the data. Now, going to the performance, here on the left plots, you see how the CNN algorithm compares with the standard shower axis prediction. So this is 10 to 20 TeV deposited energies in the colorimeter. By eye, you can see that the performance is much better with the convolutional neural net. Also, on the right-hand side plots, you see comparisons with the data. In the data, we can all these plots, so they're in terms of particle intercept and predicted particle intercept and azimuthal angle. So we compare the predicted values against the truth. When we do comparisons with the data, of course, there is no truth. So we take a reference track from the tracker, reconstruct it with standard techniques. We just need an additional event cleaning to make sure that the track in the tracker corresponds to the truth. So we take very clean events when you don't have large multiplicity of hits. So we are sure that the track reconstructed in the tracker corresponds to the truth. And there you can do comparisons with the data. And again, you see a very good agreement, which indicates of reliability of our algorithm. I remind you that it's trained on Monte Carlo, so it's very nice to see that it actually matches to the data. It means our colorimeter is pretty well simulated. Now going to some numbers. On these plots, we show 68 and 95 containments when you take predicted particle direction against the truth particle direction or the reference tracking STK. Again, in terms of intercept, so in millimeters, or angle in degrees. On the left side, these are plots for hadronic showers, and on the right side for electromagnetic showers. As you can see, at up to few hundred GeV for hadronic showers, the improvement with CNN is marginal. But then when you move towards higher energies above 1 TeV, there is really a big step. So you have an average improvement factor of 6. For electromagnetic showers, this improvement already starts even at lower energies, at a few tenths of GeV, and then at TeV level, you have an improvement of factor of 7, 8. Okay, so we managed to do a very nice particle direction prediction in colorimeter. Now we can move to the tracker. And here, the approach that we choose is as follows. So we take the direction from the colorimeter, we project it onto the tracker, we define a region of interest, which is in our case plus minus 1 centimeter. We collect hits in the tracker in this region of interest, and we convert it to a Hoch image, which you can see on this plot. And then again, we have another convolutional neural net, which we ask to predict the actual primary particle position on the Hoch image. The architecture of this network you can see on these slides. We have 4 images, 2 images for XZ projection of Dampe, 2 images for YZ projection. In each projection, we have separate image for hits that have high signal, which is likely attributed to helium or other ions, and image for the low signals, which are likely attributed to MIP particle, proton or electron. Architecture of neural net is not very much different from the one of colorimeter. However, we have an image reduction level to reduce the dimensionality. Then when this network predicts the particle direction, what we do is we simply take this direction and associate hits in the tracker to this direction. Simple distance matching within a certain window, which in our case is 0.3 millimeters. So we just take the closest hits. And this is our track in the end. Here we don't do any fitting. So there is no Kalman fitting or anything. We just predict direction and then we associate hits to this direction. To quantify the performance of our tracking algorithm, we calculate efficiencies. We do it as follows. So we take proton and helium Monte Carlo. We take truth particle direction and calculate absolute particle charge in the tracker, given the truth direction, in a certain window. And then we take the same window and calculate how many events we get if we use reconstructed track instead of the truth one. And then we can take a ratio of 2 numbers, and this will give us this efficiency. So on these graphs, you see comparison of 3 algorithms. The gray graph corresponds to a standard tracking with the standard identification algorithm, the one that we used in our publications for helium spectrum measurement. Then the blue graph corresponds to the standard tracking with the ideal identification. So when on Monte Carlo truth level, you match reconstructed track to the true direction. And then the black one corresponds to the developed convolutional neural net. As you can see, if you look at the blue graph, which is the standard tracking, if you would have an ideal selection, it still does a decent job at lower energies, below 100 TeV. But then anyway, the efficiency falls almost to 50%. And anyway, you don't have an ideal selection algorithm existing. So here the gray graph is the standard selection algorithm, which is optimized multiple times. So people really did a lot of work to optimize this algorithm. Still, you don't have an ideal selection. While for CNN, or for this black graph, we don't even need selection. We have only one track, which has a very high efficiency. So the efficiency is on 98–99% level, and it drops slightly to 96–97%. And we believe this can be recovered by increasing the statistics of Monte Carlo at highest energies at the training. One last thing that I didn't mention before, if we want to do an absolute charge measurement, we also need to make sure that particle does not interact inelastically before the tracker. This is a typical type of selection that we do in our experiment, and normally we do it using plastic scintillator detector. So there we look at the charge difference in different plastic scintillator levels to ensure the consistency of charge, and that tells you if particle interacted inelastically or not. However, this conventional method does not do a good job at high energy. So on the ROC curve that you see here, the gray line corresponds to the standard algorithm that rejects inelastically interacting particles. So if we want to go to PV energies, we need a reliable algorithm that efficiently rejects inelastic interactions. And here we profit of the developed approach. So we basically use similar type of neural network, in this case as a classifier. The only difference is that we use both raw image of the tracker and the Hoff transform image of the tracker. And this neural net makes a prediction whether a particle interacts inelastically or not. And the corresponding black ROC curve, you can see that outperforms significantly the standard algorithm. Now, as we have all pieces together, so we have colorimeter neural net prediction, we have tracker neural net prediction, and we have inelastic interaction classifier, again, based on neural nets, we can apply it to the data. And on this, here you can see the distributions of particle charge reconstructed in the tracker using our CNN approach. And red line corresponds to the Monte Carlo. Visually by eye, you see that proton and helium peaks can be clearly identified up to highest energies. So for instance, in the last energy beam, 50 to 100 TeV, this is a deposited energy up to 100 TeV. It corresponds to real particle energy of few hundred TeV, actually, or even PeV. There are also PeV particles falling into these energy beams. Also for comparison, the gray distributions show data selected with the standard algorithm. And also there is a gray dotted distribution which shows standard tracking algorithm if no inelastic interaction classifier is applied. So you can see how much cleaner, even by eye, you can see how much cleaner proton and helium signatures we can get from the data. And then on the right-hand side plot, we also do comparison of efficiencies with the standard tracking and with developed CNN algorithm. So we can take the ratio of two efficiencies and compare data in Monte Carlo. And you can see that this data Monte Carlo difference is within 1–2%, and it falls conservatively within the systematic error bound. This systematic error, by the way, is attributed to the standard track identification and procedures related to it. So there is no systematics of CNN in this. So this also gives us confidence that the algorithm works and it works on the real data, actually. So now the next step is apply the algorithm in the actual physics measurement. So if you remember my first slides, I was talking about proton and helium spectrum measurement. Now we can move it further. We can move it towards the PV frontier. To summarize, DAMP and HERT instruments represent the state-of-the-art of cosmic ray physics in space at highest energies. And HERT is actually a next-generation mission. Sorry. These experiments share the same ideology when you have thick colorimeter inside and it's surrounded by tracker. They're capable of unique measurements up to PV scale. However, these measurements are impossible with conventional tracking. That's why we developed a novel. This is the first time that a completely machine-learned tracking pipeline is developed for space instruments. And as you can see, it shows very high efficiency, about 96%. There is no need for track identification. There is good agreement with the data. And as an interesting outcome of the project is that you can reconstruct colorimeter shower axis much more precisely with neural nets compared to the standard analytical algorithms. This is a side product of the project, but it's a very interesting one. And finally, I would just like to say a word about, I would like to thank all the civilized world to the support of my country in this very heavy moment, and say that we really appreciate it, and this support is vital for the future existence, and therefore also for my personal research and research in our group, for all those Ukrainians who participate in it. Thank you.
So it's time for questions in the room. Say your name.
Yeah, Joachim. Thanks for that interesting talk. I'm only experienced with ground-based cosmic astronomy, and I was wondering how you get your statistics, because I imagine your aperture can't be too large. So how do you collect a lot of that high energy cosmic particles?
Well, when you talk about ground-based experiments, you usually deal with much higher energies. So we talk about the energy region, TeV-PeV scale. This is actually a connection between direct experiments in space and ground-based, because ground-based experiments are usually if you look at the measurement, they go beyond PV scale. That's why their statistics is much lower. And then the cosmic ray spectrum, it falls as energy in the power of 2.7, so it falls very dramatically. That's why at TeV-PeV, let's say at 10 TeV, 100 TeV, you can still, even with small instrument, relatively small instrument like DAMPE, you can collect a lot of data. So there is, it's just a matter of power law spectrum of cosmic rays.
Andrei, many thanks. I had a question for your choice, just to see if I understood this correctly. The reason you consider the CNN here and not a graph-based solution is that you are actually not, you're not interested in the many tracks to find. Your output feature you predict is a representation axis of the one particle that points back to the tracker. Is that
yes,
correctly? Yeah, and that's why the CNN probably could be more powerful, because you take, let's say, more pixels into account than if you have to construct the graph first out of them. Because if you construct the graph, you need to kind of assign nodes to the single pixels, which you don't have to do here. So I think that might be the key why this works well, at least in my head.
Yes, I would say it's largely correct answer. Also, we don't have complex topology of events. So you have a primary particle, primary cosmic rays, and then you have a lot of secondary particles, but they're mostly basically they all look like straight tracks. We don't have magnetic field. Even if you would have magnetic field at this energy, the curvature will be 0. So they all look basically the same. For us, Hawk image was a natural first choice to try it. We thought about graph neural nets, but let's say the idea was that if Hawk transform cannot and subsequent neural net cannot do a good job, then we will move to graph neural nets. But our results show that this is not needed. I mean, we will already get to a level of 1-2% inaccuracy, and it is not likely that we will need to go further.
Yeah, I think, just to repeat, I think if you want to construct a graph, you will have to do the same as you did with your classical algorithm. You need to define what's the node and what's the node is one measurement. So when you use a CNN, you don't have to do this decision, and you have that's probably broader information flow into the dense layers. What I think.
Also, Andy, the detector is, I mean, the slide before this one, the detector is a regular bridge, so yeah. That's a good application of the CNN. least the plot slide 50.
Okay, so Marcus?
Yeah, thanks for the interesting talk. I have to ask a really stupid question. You probably said that, but I somewhat missed the point. It's really a question about understanding, because you talk about ionization measurement in the tracker for PeV particles. That doesn't work with DDX, right? I mean, so somewhere in the middle between the shower displays and the energy loss per hit, I lost some connection on how that's working. But maybe it's really a stupid question.
Yeah, sorry, probably I was not very clear here. So the idea is that dE over dx, it's a standalone thing. So we let's say we need a perfect track reconstruction in order to know precisely where our particle pass through detector. So if you look at this plot, basically you see a lot of hits. So we need a precise track direction to identify which exact hit out of this belongs to a particle. And then if we can do this, then we measure precisely dE over dx, also because you have up to 12
but beta block for you are in saturated at PeV, no matter what the particle type is. I mean, that's so far out.
No, why are you saturated?
At beta electron volts.
I mean, the ionization loss, there is no shower. I mean, the shower starts at least after the first layer of the tracker. So we can measure the ionization loss.
I'm still missing something.
I mean, it does not depend strongly on particle energy, right? I mean, if you look at this plot, so this is the ionization loss. So this is what, sorry, this is what you get at 50 TeV, and this is what you get at 500 TeV. The signal is nearly the same.
Yeah, this because you're on the DEDX plateau. So the question is whether the particle, the particle mass is big enough to separate the bands. But I don't know, because I've never looked into this regime.
You have the factor 2. Is this affecting something or not?
No, it's as I say, it's almost. I mean, these are numbers from Jean's simulations. And I mean, you pretty much get the same in the data. I'm sorry if I didn't get it, but
I don't know if there was there some question on the chat or not?
No one on Zoom.
There's another question in the room.
Hi, I'm Andre. Where do you do the processing of this? Is it done on the device in space, or is all the data sent down to Earth and processed there?
It's all done offline. So the data is sent to data center in China, and then all this machine learning processing we already do in Europe. Actually, we do it on the analysis level. So we have a tool. We don't even do it for now at the data reconstruction. We have a tool that does it on the fly on the analysis level.
Okay. Thanks. Well, thanks, Andrea, again. But let me say that I think we all here in the room we are sympathetic with your cause, and also we support the